Okay, so we'll start with Robin Lorenz, who will talk about quantum causal model, and he will make an introduction and an overview.
All right. Does this work? Great. Yeah. Thank you very much for the introduction. Good morning, everyone. And thank you very much for the invitation to speak at this amazing conference. I'm very much looking forward to this. So let's dive in, because there's a lot to get through today. What is this about? Well, there's this framework of causal models that I'm sure most of you will be familiar with. It's, these are the early protagonists, but many have contributed since. This is big, I think, having spelled out how causal claims relate to empirically accessible objects like probabilistic statements involving interventions and observations is the foundation of, of causal discovery and answering other causal queries. And this is important in practice, from medicine to social sciences to AI and machine learning. The work by Joshua Bengio and Bernhard Schulkopf and Dominik Jansing is fascinating here, and important for philosophy of causation. So I think this is big, and as I probably won't have to explain to this audience, physics challenges our causal concepts. For one thing, Bell's theorem can be seen to imply the causal inexplicability of Bell correlations in terms of space-like separated measurements in just a common cause and the common past. This argument is subtle, but the bottom line is that this framework of causal models that formalizes our causal intuitions is not able to give satisfactory explanations. Also, the study of quantum gravity and of indefinite causal order, just mentioned, challenges our intuitions. It's probably worth emphasizing here that there are different notions of causality that physicists mean when they say causality. So one might study how the structure of space-time implies constraints on what can possibly be causally related to what, to be in keeping with relativity, but that doesn't tell us what actually is causally related to what, or what that relation should be in the first place. So in this talk, I won't be talking about indefinite causal order or how systems are embedded into some space-time, but focus on this basic notion of causal relation. So basically at this turning point where one has to decide, do I just throw away all of causal reasoning and give up and say quantum correlations are not amenable to be understood in causal terms, or is there a new type of causal relation appropriately lifted to quantum theoretical terms? And that involves some very basic foundational questions like, when A is a cause of B, what sort of thing are A and B? What are the relata? What is the causal relation, and relative to what data is it defined? Does causation pertain only to a classical world? How does this alleged asymmetry sit with fundamental physics? And what's the role of agents? A quantum causal model framework should either start from answers to these questions, provide them, or at the very least provide the basis so as to discuss the different possible answers in a more meaningful way. It should incorporate our intuitions that we might have anyway about the Bell scenario, and maybe eventually also help better understand this phenomenon of indefinite causal order. Eventually, we might also hope it helps delineate what aspects of this quantum generalization of causal relations can be done in an, let's say, interpretation-independent way, just on the basis of the quantum formalism, and which aspects would require taking an interpretational stance, and thereby sort of developing a causal perspective on foundational questions. That's at least the ultimate hope. This talk will be much more humble. I'll just give an introduction and overview into this framework of quantum causal models based on these three works here you can see. Apologies if you have already seen lots of talks about this in the past few years. Usually, the story proceeds something like this, starting from classical causal models, sort of then thinking about causal principles therein, identifying a special case, the Reichenbach's common cause principle, and then going backwards and generalizing that to quantum. I like this story, but it's not what not the approach that I'll take today. Rather, I'll take a quantum-first story. So, apologies again if you have seen John Barrett's talk at the Simmons Institute earlier this year. My talk will not be the same, but very similar, just not as eloquent. And what I mean with quantum first is the following. So we'll start from defining the quantum causal relation and causal structure, from which then, and that's the argument, the rest will follow sort of naturally, in particular definition of a quantum causal model, some generalizations of other aspects of this classical framework, and what I call diagrammatics, sort of studying a compositional understanding of causal structure. Okay, so let's start. Causal influence, and yes, for simplicity, only finite dimensional systems in this talk. Given a unity from AB to CD, we say A does not influence D if this condition here holds, and probably you're all very familiar with that. There are lots of equivalent conditions, one could say. In particular, the marginal state at D is independent from the state at A, no matter what the state at B. And, it's negation. When there actually is influence from A to D, we say A is a direct cause of D. Now, this condition is also equivalent to that an agent stationed at A cannot signal to an agent stationed at D. And as such, a no signaling condition makes sense for arbitrary channels, CPTP maps. So that raises the question, why insist on this data be unitary for the definition of a direct cause relation? And this argument has been given many times, but because it's crucial for today, let's just recall here a basic example. Here the quantum C0 gate is a unitary between qubits, labeled AB and A prime, B prime at the later times. Then there is influence from A to B prime. And we all agree on that, and in that case we're happy to assert that there is influence from A to B prime. However, if an agent at A ends up, for some reason or other, to assign a maximum mixed state to the system at B, then as a matter of fact, the channel through which this communication will go is the one on the right, so there is no signaling whatsoever. And that's an instance of fine-tuning, such as is not uniquely quantum, it exists just as much classically. And the lesson to take away from this is that the possibility to signal can be washed out if one doesn't account for all the interacting systems. But quantum theory does tell us how closed systems evolve, namely unitarily. So, the epistemology of causation will have lots to do with possibilities of signaling. But if the idea is to study a causal relationship, given what quantum theory is as a candidate fundamental theory of physics, then it makes sense to define it relative to how closed systems evolve according to that theory, which is unitary summations. So the possibility of signaling is a sufficient but not a necessary condition for the presence of a causal relation, is kind of the upshot. Okay, here just a bit of notational conventions for a CP map from A to B. We'll use this particular variant of the Choi-Jamiolkowski isomorphic representation. So we write these operators here, rho sub B given A, to represent that CP map, and that's a positive basis-independent operator on the Hilbert space of B in the dual of A. So just so we know what these symbols mean. Now, given a unitary transformation, in general from some n input systems, some k output systems, every output system Bj has a subset of input systems that do influence it, right? Just on the basis of the definition we just gave. Now here's a central theorem that John started calling the Uber theorem, which I suppose I'm fine with, given that my PhD was just staring at this little theorem for a long time. So it says that the CJ operator of a unitary factorizes in a particular way, namely into pairwise commuting operators of this form, each of which is representing a channel from the parents of Bj into Bj. And that they commute pairwise is a very non-trivial condition. Whenever the parental sets overlap, the operators act non-trivially on these spaces in the intersection and yet commute. And the rest of the talk, in a way, can be seen as exploring consequences of this theorem. And here's the first one, something called causal atomicity, namely that if input system AI does not influence output system Bj and also not Bk, then it is necessarily the case that it doesn't influence the joint system Bj, Bk. And contrast that with signaling in general channels, where it's perfectly possible that there is signaling to the joint Bj, Bk, but not to the individual systems Bj and Bk separately. And it's because of this property that a DAG, a directed acyclic graph, can represent the full causal structure of a unitary. All there is to be known about which systems and sets of systems can influence which others is encoded in a DAG, like in the example here. Another property of causal structure, which one can see as some consequence of this theorem, but one can arrive at that various ways, is something one might call the reversibility of causal structure. So U dagger, being a unit transformation 2, has a causal structure, and is given by just that of U by flipping all the arrows. We'll come back to that with a comment at the end. So, if you think of a unitary transformation as an evolution from some earlier system to some later system, then that already implies lots of causal constraints. So in order to talk about causal structure in general, we need a bit more general formalism. And I'm hoping that in front of this audience, I won't have to explain higher order maps and process matrices. So this slide is thought to be, again, the second and last piece of conventional notation, where it introduces process operators, so it is basically the process matrix up to our convention for the CJ isomorphism. So a quantum node A, as a locus of a potential intervention, is a pair of an input and an output Hilbert space, and then a process operator denoted as this sigma sub A1 to N over quantum nodes A1 to N, as a positive operator in this massive space of all in and output spaces of all the nodes, such that this generalized Born rule gives rise to probabilities for arbitrary choices of interventions at all the nodes. And the notation for a quantum instrument at the ith node is here this tau sub AA with outcome Ki. And then, joint states and channels and these broken circuits here on the right, they're all special cases of a process operator. It is all well known that a process operator also is the CJ representation of a channel from all the involved output spaces to all the involved input spaces. And in this example we just saw, this broken circuit, one can visualize that by sort of pulling the wires out and seeing that channel whose CJ representation is the process operator. And as such, this channel may of course be a unitary one, in which case this is called a unitary process. So you may fill the boxes with unitaries, and here's a broken unitary circuit defining a unitary process. And then it's immediate that the notion of direct cause relation we had for systems in a unitary transformation lifts to one where now the relata are quantum nodes. So given a unitary process, the node AI is a direct cause of node AJ, if and only if the output space at the ith node influences the input space at the jth node relative to that unitary process. And again, as a consequence of this Uber theorem, you might say, causal structure is then representable by a directed graph. So yes, now it is not necessarily acyclic anymore. It could be cyclic, but for the purpose of this talk, just think of basically this broken circuit, so everything will be assumed to be acyclic. And in this example, it might be like this. And just to emphasize, the causal structure is a property of the unitary process. It's not defined by this broken circuit here. The circuit implies certain constraints, but in particular here, in this causal structure, A1 is not a direct cause of A4, whereas that is perfectly compatible with the circuit we've drawn. That's a property of the process. Okay. Having defined causal relations and causal structure, the question is, what now are causal explanations? What are these causal models about? Well, the idea is that a framework of quantum causal models, on the basis of the definition just given, spells out how to give and how to check the plausibility of causal explanations of generic processes. And as such, that's perfectly analogous to an approach to classical causal models that would start from defining causal relations as functional dependencies relative to some deterministic underlying description. This quantum first story means we will not start now from classical causal models and work in analogy, but rather recover that at the end and just continue, and I hope I argue that everything kind of just makes sense. Okay. So suppose there's a process given over 5 nodes, and one asserts that the DAG on the left is the causal structure. Now, what should that mean? Well, I think it's perfectly clear what that should mean. It should mean that there is a unitary process. Well, that will involve some further systems, but not any, only such that they don't constitute further common causes. So you may have these local disturbances, these nodes lambda I for each node AI that only directly influences that node AI and no other ones. And for reversibility, basically some other node F that might be influenced by everything. And such that when marginalizing over these additional systems, you get back the sigma you started from if inserting a product state for these lambdas. And why that? Well, if it was necessary to insert a non-product state for lambda 1 and lambda 3, say, well, then the idea is that that would be because they share a common cause further down in the causal path that had better be included in the causal explanation. And that idea, that generalizes straightforwardly. So a process sigma is called compatible with the DAG over the nodes, if and only if a unitary process exists that doesn't introduce further common causes, basically, that has the right causal constraints, and such that it gives back sigma when marginalizing over all the additional nodes for some product state on these lambdas. One can show that the thus asserted unitary process incompatibility can always be realized through a unitary comb of this form. And what to make of this guy, we'll come back to that later. So, if this sigma on the left is compatible with the DAG, hence a unitary process exists, that is in the middle here, then according to the Uber theorem, that factorizes, and one can just take the traces and is left with the product of pairwise commuting operators of this form, each of which can be seen as an effective description of the causal mechanism between the causal parents and the node AI. Now, as such, this condition is one that witnesses that the set of A1 to AN is sort of a causally sufficient set, no common causes are missing, and that the DAG is a plausible causal explanation. So that is exactly what one would want to call a quantum Markov condition. So a process is Markov for a DAG G if and only if there exist pairwise commuting operators, or channels, of this form, such that when you multiply them together, you get back sigma. That's what we call then the Markov condition. Crucially, it turns out that compatibility with a DAG and Markovianity for a DAG are equivalent. So one direction we have just seen, the other one is not too hard, but I won't show here. But it's because of that this is a good notion of a quantum causal model. So given by a causal structure represented by a DAG with nodes A1 to AN, and a process sigma that is Markov for G. So in this running example we had, these two pieces of data constitute then a quantum causal model. So finally, classical causal model. So this is the only overview slide I have. It's very minimalistic. Just two comments maybe. So the analogy and the story here is the following. Given a distribution of now 5 classical variables, x1 to x5, asserting that the causal structure is as given by this DAG on the left, what should it mean? Well, we can similarly spell out a notion of compatibility and say, well, there should exist functional causal mechanisms given by functions with the domains according to the causal parents in the DAG, such that when marginalizing over these exogenous local disturbances U1 to U5 that introduce some stochasticity here, one gets back the distribution P, which then is necessarily Markov in the usual sense, everyone knows it, for that DAG. And again, it's an equivalence, this compatibility with the DAG and Markovianity for it. And then similarly, these intuitions are then encoded in the general notion of a causal Bayesian network, which is a DAG and a distribution that's Markov for it. And on the other hand, so-called structural causal models or functional models that have functional mechanisms for every variable and a probability distribution for every local disturbance. And the second comment here I make is just that these classical causal models are special cases of quantum causal models. So they live within the framework in the sense that if the process operator of a quantum causal model is diagonal with respect to a product basis of preferred bases in all the involved spaces, then that is equivalent to a classical causal model. So that said, I guess the question arises, what about all of these this rich framework full of results and definitions in the classical case. And I think I'd say that the fact that the definition of quantum causal models we've just seen makes sense is down to how it's grounded in the definition of the quantum causal relation. So wondering about these generalizations is not so much a matter of sanity checking, because a priori they don't ought to all have quantum generalizations, right? Something's going to be different quantumly. It's a matter of genuine curiosity, wondering about how far does the analogy stretch. So lots of things could be said, and probably lots of you are really familiar with the classical framework. I won't have too much time to go into detail. All I'll say here is that there are these problems of identifiability, which are all to do with some kind of data is given, can one, given what other assumptions, infer some other kind of data. And causal discovery indeed falls into that category, so given some observations, can one infer the DAG that explains it? Or given some causal assumptions and some partial observations, can one answer particular interventional or counterfactual queries? And the point is that all these problems have complete algorithmic solutions within the framework. And these algorithms use some results, some theorems. Here are a few, the d-separation theorem, do calculus, etc. But these are also results in their own right. They relate properties of causal structure with properties of probabilistic statements. So then, wondering about what goes through quantumly, I won't have too much to say on this left side, basically because it is just unfinished work. So obviously there is no observation that is informative and non-disturbing in quantum theory. We also don't stumble across process operators lying around in the world begging the question. Information in complete interventions are necessary and process tomography is costly. Nonetheless, one can define a well-defined problem of causal discovery given a process operator. What's the DAG? That is a plausible causal explanation, and there's some partial solutions to that. But more generally, one would want a problem that is non-trivial and interesting quantumly, so given by some kind of partial data that is not enough to infer the process operator. And then once one has identified the right kind of quantum causal inference problem, then work out the solution on the basis of the framework that I have presented. But this is basically just not done yet. However, on the other side, these theorems, completely independent of their utility to solve, of their role in algorithms in the classical side, they do have quantum analogues. And just to highlight what that looks like, I'll pick this d-separation theorem, because the do calculus rules would just take too long and be too involved. So I'm not sure many of you will probably be familiar with d-separation, but just to build some intuition, here, if a distribution over variables y, z, and w is Markov for either the fork on the left here or the chain, well, then that implies that y is conditionally independent from z given w. And that's intuitive, because if you hold the very thing, w, through which the correlation is underwritten in the first place, fixed, well, then there should be no association between y and z beyond that. In contrast, if you condition on w in this collider, that induces sort of an inferential way a dependence between y and z, whereas they were independent in the marginal over y and z. And then d-separation is basically just the generalization of these intuitions to a general DAG. So subset of nodes, y is d-separated from a subset z relative to a subset w, if and only if the path between y and z are of the right kind. So basically, they have to go through w with a chain or a fork, or else have a collider outside of w. That's the intuition anyway. And then the theorem says that d-separation is sound and complete for conditional independence, meaning that if a distribution is Markov for a DAG, and there holds a particular d-separation condition, then a corresponding condition dependence relation holds. The converse is not true, they're not equivalent, but completeness basically says that d-separation is the strongest possible graphical criterion you could come up with. Now, wondering about a quantum version of this, first of all, rather than, as had been done in the past, to study the properties of a probability distribution over classical variables, where the distribution arises some way or another from quantum systems, maybe through measuring or so. The idea, the spirit of this framework is to identify the right kinds of mathematical objects in quantum theoretical terms for causal structure and for the empirical description of the phenomena in which we want to understand the consequences, ramification of causal structure. So the idea would be to find a notion of independence as a property of a process operator. So we want a notion, sort of a three-place relationship that says that somehow some sets of nodes y are independent from sets of nodes z relative to some w. Maybe two notes on this here. First of all, you already see, given a process, be it classical or quantumly, you have to say something about what happens elsewhere, in these other nodes, not in y, z, w, that gives a well-defined marginal on y, z, w. With classical probability distribution, that isn't a question. You just take the marginal. It's understood. You just ignore the other variables. And the second thing is that the study of independence notions and their generalisations a priori have nothing to do with causal structure, right? Certain conditional independence relations may or may not be enforced by causal constraints. So it's sort of a thing in its own right to start with. And here is a notion that we call quantum strong relative independence. So given a process operator over y, z, and w, say that the set of nodes y is independent from the set z relative to w, if and only if sigma factorize it into two Hermitian operators that act non-trivially only on the in and output spaces of the set of nodes y and w and z and w respectively. And we call this relative independence so as not to invoke classical intuitions of conditioning on the values of variables. Why should one be interested in this notion? Well, lots could be said, but I have to be brief and only say that all the limiting cases where we would have a very clear intuition what to expect, they work out as expected. So for classical probability distribution, one just recovers ordinary conditional independence. For a quantum state, that being a special case of a process operator, one recovers vanishing quantum conditional mutual information, which otherwise is considered, the quantum conditional independence in the literature. And if W is empty, then it's just a factorization of sigma, which is indeed equivalent to the independence of outcomes of arbitrary measurements at y and z. In the special case of classical processes, there actually is a distinction, a logical distinction between strong and weak, which gives our quantum strong relative independence a name, but I won't have time to dive into that. In the general case, for general process, quantum process, and general sets y, z, w, there's an implied operational statement, which is not equivalent, so that's a bit of an open question maybe. And apart from these properties about this notion that was then identified as part of the framework, also the relationship with causal structure works out as you will now expect, namely that indeed deseparation is sound and complete for that just presented notion of quantum relative independence. And actually in the strongest possible sense, by which I mean, if a process operator is Markov for a DAG, and there is a particular deseparation condition between three disjoint sets of nodes holds, then that implies that for all possible interventions, all the other nodes outside of y, z, and w that can give rise to a marginal on y, z, and w, that relative independence notion holds. And completeness is just the same logical thing as classically. So I hope that this gave sort of the spirit of how this generalization business works, how to identify the right kind of object quantumly to reason with. And I'd like to move on to this last main part, called diagrammatics. So a compositional understanding of causal structure, I'd rather say understand quantum causal structure better. What is this about? Given a quantum causal model, so this running example that we had, by Markovianity, it's also compatible with the DAG, hence there exists this unitary process that always has a realization in terms of this quantum comb. But this is not really satisfactory. Why? Because it's not a faithful representation of the whole model. If you look at the comb, you can infer certain causal constraints, that no node can influence anyone that's earlier in the hierarchy, but can possibly influence anyone later in that order. And I'll argue that this is not a matter of aesthetics, the lack of diagrammatics for a quantum causal model. That this is a deeper conceptual thing to understand. And to contrast this with a classical case, given a classical causal model, as an example of structural causal model with functions, you can always write down a diagram, a string diagram, that perfectly and faithfully just captures the whole knowledge that's encoded in a causal model. So here, there are boxes with functional mechanisms for every function in the model, and then these little dots are copy maps. The variable sort of copied out and fed into its causal children. And it has that property that there's a connection between the output of a variable's functional mechanism into the input of another one, if and only if there's indeed a direct causal influence according to the DAG. Clearly, copy maps not being a thing quantumly, something's going to be different, right? We have to somehow figure out how systems decompose and are mediated and go to their causal children. And to understand that best is I think, by looking at just simple unitary transformations. So here's one from A1, A2 to B1, B2. And if the two no-influence conditions hold as indicated by these red dashed arrows here, well, then that unitary factorizes. And that makes the two constraints evident, right? There's no path from A1 to B2, and similarly the other way. Also similarly here, given 3 inputs and 3 outputs, if there's no influence from A1 to B3, then that implies a particular circuit decomposition that makes that fact evident. And similarly the other way here. And these facts have been known for a very long time. Just note that they're basically immediate with this Uber theorem. Then, suppose these two constraints in the middle here hold in conjunction. One can write down a circuit that always instantiates a structure like this. It always satisfies the two no-influence conditions on the left. But the converse is not true. There do exist unitaries with the causal constraints on the left that are not of the form as on the right. There is a structure that is always implied, and it's this. So this was first proven in this paper where we called them extended circuit diagrams. The semantics of these diagrams were then formalized and generalized to rooted circuits in this paper by Augustin, Claire, and John. So what's different? It's still a circuit diagram, you can say, but it's decorated with indices that are floating around, and these indices are indicating sectorial or direct sum decompositions of the spaces that relative to them, the overall map that's being represented satisfies a compatibility condition. So in this case here, if you take this slice, the Hilbert space that's associated with it, the important part is here, these two indexed parallel wires. They both have an index I, each of which are associated with a family of Hilbert spaces, and then the parallel wires don't represent the tensor product of direct sums over these spaces, but rather the direct sum over tensor products of the ith element of the left and the right family, respectively. So that doesn't contain the cross terms. And then the overall unitary that's being represented is as follows, that similarly in this middle part has this block diagonal structure of a direct sum over tensor products of Vi tensor Wi. In order to prove this, so one doesn't have to use this Uber theorem, but historically it is how it was first proven, and it maybe helps to build some intuition as to how that decomposition might come about. So if you look at the factorization of this unitary CJ operator, then this fact on the left for B1 and on the right for B3, they commute. But they act non-trivial in A2, or else A2 wouldn't be a common cause of B1 and B3. And that commutation, has algebraic consequences. It's just a well-known operator algebra theoretic result that then the underlying Hilbert space of A2 decomposes in exactly that way as up here on the right, such that this guy on the left here lives basically in the algebra that is a sum of the full matrix algebras of always the left factor, so xi left. And this second factor for B3 lives exactly in its commutant, so indeed it can be written in this form here. And there are many unitaries with their causal structures that one can decompose in this causally faithful way, by which we mean that there is a path from an input to an output in a diagram, if and only if there actually is influence through that unitary. And actually, this business doesn't care at all about how one interprets the spaces. So consider again this example of a unitary process from earlier, with this causal structure here on the left. Then that is a case where the associated unitary from output to input spaces, we do know how to decompose faithfully, and then by just basically sliding the wires around, you obtain a causally faithful decomposition of the unitary process, where similarly there's just now a path from node to node if and only if there's a direct causal influence. The indices are a bit more complex here, but the basic semantics of these diagrams are the same as before. And also, for quantum causal models, this example that we have been discussing all along, now that is a case, if the causal structure is as here on the left, that we know how to decompose and can draw now a causally faithful diagram for a quantum causal model. So the upshot is that there are many cases for which we know how to decompose unitaries, what decomposition is implied by the causal structure, but in general, it's an open question. I'd say it's a conjecture. I'd be very surprised if it is not true that the open question is that all unitary transformations, at least in finite dimensions, have such causally faithful decompositions. And if they do, then it's just a corollary that all unitary processes in all quantum causal models have one too. And I think with this, I'll wrap up to leave some time. So we've seen there is a framework of quantum causal models. It basically just use from the definition of causal relations. It's a sound and well-defined framework as far as I can tell. To do quantum causal reasoning has produced quite a few results. It is one that has the explanandum and explanans in quantum theory's own terms. Is it the end of the story? Well, no. I think there's more to be figured about quantum causation. But at the very least, it gives some clues as to how one might answer these initial questions on quantum causation that we started out on. There are various related works and generalizations that I won't have time to go really into. I'll just note the generalization to cyclic causal structure that John Ogden and I did here in this first paper. Only note that these causal decompositions just mentioned were particularly useful. It's really a theme that goes through all of the works and aspects I've presented, that understanding the relationship between causal structure and the algebraic decompositions implied by that, basically from the commutation relations from these operators of unitary CJ operator, is really crucial. And here, these causal decompositions were very useful to understand better the quantum switch and other causally non-separable processes. There's also a generalization to sectorized causal structure by Nick, Augustin, and John, where now the relata are nodes with sectorial constraints, and lots of other related fascinating work. And finally, let me just put up some open questions I see. So, for one thing, there's a question of applications, by which I mean the thing I mentioned earlier, namely identifying interesting and yet non-trivial problems of causal inference for a quantum world, and then working out the solutions for them on the basis of the framework. The conjecture about causal decompositions that we looked at last, I think working that out would really have lots of conceptual and technical consequences. And finally, in this very vague way, I put there foundational interpretational questions, and there are lots of them. How much time do I have left? 5 minutes. Okay, so I'll be very quick here, or should I leave it here and we come back? So maybe I'll just say a couple of things about this, and then you can decide what you want to ask about. So just in passing, basically, earlier, I mentioned this reversibility of causal structure, namely that the causal structure of U dagger is that if you were just flipping the arrows, which I, again, actually forgot to mention is really not appreciated always. It's not trivial, right? It doesn't, not the same hold to reversible functions classically. But anyway, that being the case, I think makes possible to conceive of a symmetric causal relationship that makes it possible to give an argument to the effect like that the debunking of a temporal asymmetry in the universe on the basis of fundamental physics doesn't necessarily lead to a debunking of causation unless one decides to just throw away all of the rich content of causation because one can't hold on to directionality. And I had also mentioned the wish to delineate which aspects of causal relations one might be able to generalize in an interpretation-independent way, and which aspects might require taking a stance. And I think that working on counterfactuals and how this notion that's so important in the classical framework might play out quantumly could play a role in exactly that context. And there are many other questions like, what do the definitions look like, or how do they make sense from the perspective of any particular interpretation? And these are the questions that we'd really love to answer, of course. And with that, thank you very much for your attention.
So thanks a lot for this very clear talk. So are there any questions? So if there are questions online, you can also raise your hand and we'll take it. And then...
Yeah, and then if I don't know the answer, then I'm sure there are lots of people more knowledgeable out there in the internet who can help answer that.
Hello.
Hi, Eric.
Hi, Robin. Thanks. Very nice talk. Just a question. Well, actually, first a comment on the counterfactuals. My student Adra will be presenting a poster. On
Excellent. I was hoping to talk to you.
Which builds upon your model.
Yeah.
Yeah, but I want to ask a question about the index circuits. Because at first we can think of those as just an abstraction, right? We're getting a certain unitary and looking at some index circuits where the decomposition is faithful to the causal structure of the unitary, but we may not necessarily think of the lines as representing physical paths of particles. But is there always a realization of such a circuit, where the paths may be realized in terms of, say, paths of particles in the suppositions of different trajectories, where the sectorial constraints have to do, say, conservation of particle number or something like that? In other words, is it all supposed to realize such a circuit where you can take literally the paths as being potential paths of particles, and the boxes, and the inputs to the boxes being physical paths?
I'm not sure. I mean, I guess in general there's no obvious or unique way to give at least one physical meaning to these decompositions, which I guess is what you're asking about.
No, not necessarily a unique way, just one but possible realization. Of course, for a particular unitary, it may not have anything to do, right?
I see.
But is it possible to realize the same unitary, at least at the abstract level, maybe even with different degrees of freedom, but just abstractly it's the same unitary, and it has that decomposition, and it can be interpreted literally as in, say, paths of particles?
That sounds right. To be honest, I haven't asked myself that question. It sounds right, but I don't know whether Augustin, who's thought lots about them, has something interesting to say about them. It sounds right to me.
No, I think you're right.
Cool. Okay, that's interesting. Thanks.
Thanks.
Any other?
Yeah, thanks, Robin. This was a very nice and clear talk. I have a question on something that you mentioned just briefly about kind of taking U dagger and reversing the edges in the causal structure, and that's not the same for reversible functions.
That's right. Yeah.
You have an intuition for that? What's so?
I don't think I myself have a particularly deep intuition about this. maybe what helps is just looking at an example, and a classical function that is reversible is the classical C0 gate. It's its own inverse, and it does not have that property that the causal structure of it is appropriately symmetric for that to work out. But I guess you're asking, why should we find that difference intuitive? And what John and Rob had said early on as well, maybe the problem is, that the world of functions is just far too big to be compared with the evolutions, according to unit transformation, of this particular theory of physics. And if you restrict to symplectic transformations, then playing the analogous role for discrete phase spaces classically, one actually does recover that that same property, and that was worked out by, I think, Isaac Friend. So that is as much as I can say, but I myself have no, deeper understanding that would make that particularly plausible.
Yeah, but that's good. Thank you. Thank you very much.
We have time for more questions. Yes. So there is a question of online. Has there been any work done in comparing the causal structure as defined in this lecture and the one introduced by the resource theory of thermodynamics?
I'm sure there has been done, but I'm afraid I'm not the person to answer this question. I'm sure there are people in this audience who know the answer very well to this, but it's not me. So sorry, I have to pass on this. Unless someone here wants to answer the question.
We have time for one more question, and then there is the break.
Thanks very much for your talk.
Sorry. Hello? What?
Okay. Thanks very much for your talk. I'm not from this community. I work in high energy, and I've never seen the diagrams that you showed us before. I'm sure everyone else in the room has, but I have a feeling that they're going to come up a lot in this conference. So if you have time, do you mind explaining the first diagram and what it means? Or maybe it's better if you explain to me later if everyone else knows what's going on.
That might make more sense. I think you're right. They will be coming up quite a bit, probably. I'm very happy to chat over the break and talk about these.
Okay, thanks very much.
Yeah, sorry about that. I wasn't quite sure what to expect in terms of audience.
Okay, well, one more question.
Okay. Concerning the diagrams with the labeled things,
yeah.
I read some papers about many worlds calculus and how like the product structure, or the sum structure is an additional feature in these diagrams. And then every wire is labeled by some world. And I think it's related to this labeling here. So yeah, I think it also relates to Eric's question. So yeah, I think it's, so there the labeling is really to allow for superpositions. So I think, yeah, it's an interesting link with this thing. So
yeah, I think this is a good point, and indeed, John has been for a while expressing speculations about giving an interpretation to these indices in a quantum theory interpretation sense, and to make them much more than what they're here in terms of just the mathematical decompositions. And one way would be sort of in a many worlds interpretation, but could be something else to see how somehow classical outcomes are associated with the indices taking values. So that's something he's talked about in the past. It was a very good observation, I think.